Voyager 1 has been in interstellar space for over a decade, but the instrument built specifically to confirm that crossing had been dead for 32 years before it happened. That is not a metaphor. It is the operational fact that defines everything that follows. The plasma science instrument aboard Voyager 1, a device purpose-built to measure plasma density, the precise property that would prove the spacecraft had crossed the heliopause and entered the interstellar medium, failed in 1980, shortly after the Saturn encounter. It never recovered. For the next 3 decades, as Voyager 1 travelled outward through the heliosheath, through the turbulent compressed zone beyond the termination shock toward the boundary of everything the Sun controls, its most critical sensor was gone. The machine that would eventually cross into interstellar space did so without the eyes it was designed to use. So how was the crossing confirmed at all? The answer involves a man named Don Gurnett, a solar storm, and an instrument doing a job it was never designed for. Gurnett was the principal investigator for Voyager's plasma wave science instrument at the University of Iowa. His instrument was built to detect oscillations and wave behavior in plasma, not to measure plasma density directly. Those are related but distinct capabilities. A microphone and a scale are both useful in a kitchen, but they are not interchangeable. Gurnett's instrument was the microphone. What the team needed was the scale. After 1980, the scale was gone. In April 2013, something unexpected provided a workaround. A solar coronal mass ejection, launched from the Sun in 2012, travelled approximately 18 billion kilometres across the heliosphere and beyond it, eventually reaching Voyager 1's position. When the wavefront arrived, it disturbed the local plasma caused it to oscillate. Gurnett's instrument registered those oscillations. From the frequency of those oscillations, the team could infer plasma density indirectly, the value they calculated, approximately 0.08 electrons per cubic centimetre, roughly 40 times denser than what the outer heliosphere produces, consistent precisely with the interstellar medium. The methodology was sound. The physics connecting oscillation frequency to plasma density is well established. But the measurement was indirect, made by an instrument operating outside its primary design parameters, triggered by a solar event rather than by the medium itself. The scientists acknowledged the margin of uncertainty. They did not overstate what they had, and the number held. What makes this sequence stranger still is the timeline. The crossing itself, later dated to the 25th of August 2012, had already happened 8 months before this confirming measurement arrived. Nobody announced it in real time. The data in the weeks and months around the crossing was ambiguous. Sharp swings in cosmic ray counts, partial reversals, patterns that could mean a crossing or could mean a fluctuation near a moving boundary. The team waited, they studied, they disagreed, and then the Sun, in its own time, provided the perturbation that settled the argument. The formal announcement came in September 2013. NASA held a press conference. Ed Stone, who had been Voyager's project scientist since 1972, 41 years by that point, stated plainly, "This is a historic day for humanity. We have left the solar system. We are now in interstellar space." Don Gurnett spoke too. His words were precise, and they carry more weight when you remember he was describing what his wave instrument had found, not the plasma instrument that was supposed to make this measurement. "We're in a completely new region," he said. "This is plasma that has never been touched by the Sunday." The instrument that made that statement possible was not supposed to be doing that job. The scientist who built it spent the final decade of his career watching its data rewrite what we thought we knew about the boundary of our solar system. Gurnett died in 2024. Now consider what the spacecraft is actually doing as it sends that data back. Voyager 1 transmits at approximately 160 bits per second. A fax machine from 1985 was faster. The signal, travelling at the speed of light, takes between 22 and 23 hours to cross the distance from Voyager 1 to Earth one way. Ask the spacecraft a question. Wait nearly a full day for the signal to arrive. Wait another nearly full day for any response to return. The machine was designed to operate for 5 years. As of 2025, it has been operating for 47. The contrast is almost structured like a proof. The instrument designed to confirm the most important measurement of the mission failed after 3 years. The spacecraft it was mounted on has kept working for 47. The sensor the engineers counted on is silent. The machine they built to carry it is still transmitting. This film is not about what we sent into space. It is about what came back. What came back was data from a place no instrument had ever directly sampled. What came back was a plasma density, a magnetic field reading, a cosmic ray flux measured at full interstellar strength for the first time in history. And what came back was strange. The boundary did not behave the way the models said it would. The magnetic field did not rotate as predicted. The medium between stars turned out to carry its own persistent hum, a continuous oscillation at roughly 3 kilohertz, detected in 2021, still present today. Not silence, not void, something with texture and frequency and density. None of that is what the mission was designed to find. The mission was designed to study Jupiter and Saturn. The instruments were designed to measure a solar system that turned out to be only part of the story. The paradox that runs through everything that follows is visible right here at the start. The piece of the spacecraft built for the decisive moment did not survive to see it, and the decisive moment happened anyway, confirmed by an instrument pressed into service beyond its specifications, triggered by a storm from a star 18 billion kilometers away. That is not a story about equipment failure. That is a story about what science actually looks like when it reaches the edge of what any of its tools were built to reach. Voyager 1 weighs approximately 825.5 kilograms, less than a mid-sized family car. Its high-gain antenna dish, the structure that points back toward Earth and carries every measurement it has ever returned, spans 3.7 meters across. Not a building, not a ship. A disc slightly wider than a standard doorway is tall, mounted on a frame that fits inside a modest garage. These are not the dimensions of something designed to outlast its builders. They are the dimensions of something designed to survive 5 years. It launched on the 5th of September 1977 from Cape Canaveral, Florida, carried out of the atmosphere on a Titan 3IE Centaur rocket. Voyager 2 had already left 16 days earlier on August 20, but Voyager 2 was aimed on a slower trajectory, one that would allow it to continue from Saturn toward Uranus and Neptune. Voyager 1 took a faster, tighter path. It overtook its twin. The second spacecraft to launch became the first to arrive. That is not a trivia footnote. It is a small illustration of the logic that governs everything in this story. Trajectory determines fate, not sequence, not size, not the order in which you begin. Inside Voyager 1, the primary brain is a flight data system with approximately 69.63 kilobytes of memory, 70,000 times less than a modern smartphone. The processor was built from early 1970s technology, already a generation behind the cutting edge when it launched, because design had to begin years before the launch window. It has never been upgraded. The same circuits that processed the first images of Io's volcanic eruption in March 1979 are processing readings from the interstellar medium today. Not a successor system, not a patched upgrade. The same physical hardware. The power source is 3 radioisotope thermoelectric generators, each loaded with plutonium, 238. At launch, the RTGs produced approximately 470 watts combined. That number has been falling ever since, at a rate of roughly 4 watts per year as the plutonium decays. By 2025, the estimated output is somewhere between 249 and 260 watts. A handful of LED light bulbs draws comparable power. The craft, travelling farther from Earth than any object humanity has ever made, is running on less electricity than most kitchen appliances left on standby. And the decline does not stop. The RTGs are expected to fall below the threshold needed to power science instruments sometime in the mid to late 2020s, the exact date depending on how JPL manages the power load across the remaining active instruments and which systems get switched off to preserve the others. Engineers have been watching this horizon for years. The approaching silence is not a surprise. It is a slow countdown written into the physics of radioactive decay, visible from the day the spacecraft launched. Consider the operating parameters together. 17 kilometers per second relative to the Sun, roughly 61,200 kilometers per hour. Every day, the gap between Voyager 1 and Earth widens by approximately 1.6 million kilometers. Its current distance is somewhere between 163 and 165 AU from the Sun, a number already larger by the time these words are read. It transmits at 160 bits per second across a signal travel time of 22 to 23 hours one way. The machine is real-time in the way that continental drift is real-time. The physical absurdity of this object needs to sit still for a moment before its achievements do. Something that weighs less than a car, runs on less power than the lights in a small apartment, carries a processor that a 1980s pocket calculator would not envy, is currently farther from Earth than any manufactured object in the history of the species, and is still sending data. What Voyager 1 has accomplished is not a triumph of engineering scale. The Apollo Saturn V was engineering scale 36 stories tall, 3.4 million kilograms at liftoff, generating 7.5 million pounds of thrust. Voyager 1 is the opposite of that. It is what happens when a small, precisely aimed object is given enough time and a trajectory that nothing can interrupt. Its achievement is not power. It is persistence along a line nobody else has travelled. The design lifetime was 5 years. The outer planets were the mission. Saturn was the last planned destination. And even reaching Neptune Voyager 2's eventual target was considered an ambitious extension, not a certainty. Nobody designed the spacecraft to cross the heliopause, because in 1972, when the design work began, the heliopause was a theoretical construct at an unknown distance, and the idea of a spacecraft surviving long enough to reach it was not the basis for any engineering specification. 5 years was the contract. Everything after that was borrowed time. 47 years in, the machine is still operating, still transmitting, still extending what human instruments have directly measured. Every year of operation past 1982 was a year nobody planned for. Maintained by a team that has had to adapt continuously to a spacecraft aging in ways its builders could not fully anticipate, and a communications environment, the interstellar medium that no one had designed its instruments to navigate. What did it find in all those extra years? That question drives everything that comes next. The planetary encounters were the mission. The decades of travel that followed the Termination Shock, the heliosheath, the Heliopause, and the medium beyond it were the bonus that turned out to be the point. The car-sized machine is still out there, still moving, and for now, still talking. In the late 1960s, a JPL mathematician named Gary Flandreau noticed something in the orbital mechanics data that almost nobody had registered. The outer planets, Jupiter, Saturn, Uranus, and Neptune, were drifting toward a configuration that occurs approximately once every 175 years. For a brief window in the late 1970s, they would be positioned so that a spacecraft launched from Earth could fly past each one in sequence, using the gravity of each planet to bend its path and accelerate it toward the next. No additional propulsion required after the initial burn. No impractical fuel load, just trajectory, timing, and physics. This was not a shortcut. It was the only route. Without that alignment, a direct mission to Neptune would require either decades of travel on a slow arc or a fuel mass so enormous that no rocket of the era could carry it. The outer solar system, in practical engineering terms, would have remained unreachable. Flandreau's calculation opened a window that the laws of orbital mechanics had been slowly closing for generations and would close again before anyone alive in the 1970s would see it reopen. The underlying physics is exact. When a spacecraft passes close to a planet, the planet's gravity pulls it in, curves its path, and if the geometry is correct, flings it outward at higher speed. The spacecraft gains kinetic energy. The planet loses an equivalent amount from its own orbital momentum, slowed by an amount so small it cannot be measured against the immensity of the planet's mass. Jupiter loses nothing detectable. The spacecraft gains everything it needs to reach Saturn. Saturn then does the same for the next target. Each flyby is a slingshot loaded by a world. The window for this particular alignment was narrow. The spacecraft had to launch in 1977, a few years early, and the geometry was wrong. A few years late, and the planets would have drifted out of position. The opportunity closed, and the next one would not arrive until the 2150s. The engineers at JPL in Pasadena understood this. The mission design was built around a deadline the solar system itself had written. They called the concept the Grand Tour. JPL began design work in the early 1970s, which meant the spacecraft's electronics reflected what could be manufactured and qualified for space in that decade. Integrated circuits were in their early commercial years. Software was written and tested on hardware that would seem primitive by almost any subsequent standard. There was no option to wait for better technology. The window would not wait. The 1970s electronics were not a compromise. They were the only available material from which a spacecraft capable of launching in 1977 could be built. Now, for the numbers that will frame everything else in this film, distances in the outer solar system are not usefully expressed in kilometers alone. The figures become too large to hold. Scientists use the astronomical unit, abbreviated AU. 1 AU is the average distance from Earth to the Sun, approximately 150 million kilometers. Mars orbits at about 1.5 AU. Jupiter at roughly 5.2 AU. Neptune, the outermost major planet, at approximately 30 AU. The Heliopause, the boundary of the Sun's influence, where solar wind gives way to the interstellar medium, sits at a distance Voyager 1 crossed at approximately 121.6 AU. Convert that, roughly 18.2 billion kilometers from the Sunday, not 18 million, billion. In light travel time, a signal from that boundary takes more than 16 hours to reach Earth. Voyager 1's current position is approximately 163 to 165 AU and widening every day at 1.6 million kilometers. To reach the nearest star system, Alpha Centauri, at 4.24 light-years, travelling at its current velocity of 17 kilometers per second, would take roughly 70,000 years. It is not heading toward Alpha Centauri. Its path points toward the constellation Ophiuchus. The closest stellar pass it will ever make the star AC plus 793888, in roughly 40,000 years, will bring it no closer than 1.6 light-years. That is not an arrival. It is a miss measured in trillions of kilometers. And long before 40,000 years, the machine will be silent. The RTGs will exhaust their useful output within this decade. After that, Voyager 1 continues moving. It cannot stop, but without power to run instruments or transmitters, it moves without a voice. All of this from a spacecraft whose designed mission was 5 years. Jupiter and Saturn were the targets. The Grand Tour, in its full 4-planet form, was eventually descoped by budget constraints. The funded mission was Voyager 1 to Jupiter and Saturn, period. Uranus and Neptune were assigned to Voyager 2 on a separate trajectory. Interstellar space did not appear in any mission specification, any budget justification, any engineering requirement. It was a theoretical destination that might follow if the spacecraft survived long enough, if the instruments held, if funding continued, if the teams stayed together. None of those conditions were guaranteed. All of them improbably held. After Saturn, Voyager 1 had no more planetary targets. Its trajectory carried it northward out of the plane of the solar system, a consequence of the Titan flyby, which will be addressed in its own chapter. And from that point forward, the mission was extended not because a destination existed, but because the machine kept working. Each year of continued operation was a year beyond the terms of the original contract with gravity and time. The mission was not conceived as an interstellar probe. It became one by accident of trajectory and survival. Those two things, where it was pointed and the fact that it did not fail, combined over decades to produce something nobody had planned. The first instrument in human history to cross into interstellar space and transmit measurements back. What you sent into space was a Grand Tour spacecraft aimed at Jupiter and Saturn. What you got 47 years later was the only direct measurement of the interstellar medium ever made. The distance between those two facts is 175 year windows and borrowed time. 3 days before Voyager 1 made its closest approach to Jupiter, a paper appeared in the journal Science. Its authors were Stanton Peele, Patrick Casson, and Ray Reynolds. The argument they made was mechanical. Io, the innermost of Jupiter's 4 large moons, is caught in a gravitational tug-of-war between Jupiter itself and the neighbouring moons Europa and Ganymede. Those competing pulls continuously flex and deform Io's interior, generating heat through friction, the way a bent paperclip grows warm at its crease. Peele, Casson and Reynolds calculated the magnitude of that heating and arrived at a conclusion they published on the 2nd of March 1979. The tidal forcing, they wrote, was sufficient to drive active volcanism on Io's surface. 3 days later, Voyager 1 swept past Jupiter. The paper had been in the scientific community for 72 hours. Most people who would have read it had not yet read it. The spacecraft did not wait. Linda Morabito was not looking for volcanoes. She was a navigation engineer at JPL, and her assignment in the days after the Jupiter flyby was methodical and unglamorous. Examine post-encounter images of Io, identify background stars in the frames, use their positions to refine the spacecraft's precise trajectory for the road ahead. Navigation work, the kind of task that generates no headlines and produces no discoveries. She was looking for pinpoints of light in the dark behind the moon. One image stopped her. Rising above Io's curved limb was a crescent-shaped plume. It extended approximately 270 kilometers above the surface, taller than most of Earth's atmosphere, is wide, curving outward into space in a shape that had no business being there. Morabito's first thought was practical and grounded. Another moon, positioned behind Io, its edge protruding into the frame. She cross-checked the geometry. No moon was at that position. No moon could produce that shape. The room she was working in began to fill with people. What Morabito had found, while searching for background stars to calibrate a navigation calculation, was a volcanic eruption on another world. The first active extraterrestrial volcanism ever observed by any instrument anywhere in the history of human science. Not theorized, not inferred from ancient geology, witnessed. Before this moment, the working assumption about Io was reasonable and entirely wrong. The moon's surface was expected to be cratered and cold, ancient, battered, geologically quiet. Bodies that small do not retain internal heat for billions of years. They radiate it away. The solar system was supposed to have sorted this out long ago, leaving the small moons as dead rock. Ed Stone, Voyager's project scientist, put it directly. We expected to find a dead, cratered moon. We found the most volcanically active body in the solar system. Over the course of the Jupiter encounter, Voyager 1's instruments confirmed 8 to 9 active volcanoes distributed across Io's surface. Not remnants, not calderas suggesting past activity. Active, erupting into space, continuously reshaping the moon's surface with fresh sulfur and silicate material, erasing impact craters faster than they can accumulate. The reason Io has almost no craters is not that it has been spared, it is that its surface is perpetually being buried and replaced. Every model of Io built before March 1979 was describing a moon that does not exist. Now consider the timing, because it does not improve with familiarity. Peel, Casson and Reynolds published their prediction on March 2nd. They identified the correct mechanism, tidal heating from Jupiter, and the resonant orbital pulls of neighbouring moons. They derived the correct conclusion that this heating was sufficient for volcanism. They had not seen a single frame of Voyager 1's flyby data when they wrote those words. Their paper was theoretical, based on orbital mechanics and thermal modelling. Then a navigation engineer found a volcanic plume in a routine starfield image 3 days after the paper appeared, and the two events collided in the same week. When the authors of that paper saw Morabito's image, they understood immediately what they were looking at. Their prediction had been confirmed in real time by someone who was not a volcanologist, who was not studying Eo's geology, who was not looking for any signature of internal heat. She was locating stars. The confirmation came through the wrong person, doing the wrong task, using the wrong image. That is not a failure of the scientific process. It is what the scientific process actually looks like when the universe cooperates with the method while ignoring the personnel assignments. The lesson Io establishes here is one that will hold for everything Voyager 1 finds from this point forward. The critical measurements do not arrive through the instruments built to make them, or the scientists assigned to interpret them, or at the moments designated for discovery. They arrive through instruments doing something adjacent, through engineers doing routine work, through detections that require the observer to stop and check whether they have made an error before accepting what they are seeing. Morabito checked. She was right. The universe had concealed the most volcanically active body in the solar system from every telescope ever pointed at it, because from Earth's distance, Io was a smear of light with no resolvable surface. It took a spacecraft 349,000 kilometers from Jupiter's cloud tops, returning images for navigation purposes, to make a discovery that reordered the entire category of what small moons are capable of. Not because anyone planned for this specific finding, but because the spacecraft was there, the instruments were running, and someone was paying careful attention to a task that was supposed to be administrative. The question the Io discovery leaves open is not about volcanoes. It is about every other moon, every other body in the outer solar system that has been observed only from inside Earth's atmosphere through instruments that flatten and blur the detail. How many dead, cratered, geologically quiet moons are not? Io was not the only thing Jupiter had been hiding. In the hours around closest approach on the 5th of March, 1979, 349,000 kilometers from Jupiter's cloud tops, Voyager 1's cameras and instruments were running continuously, capturing everything they could reach. The mission had specific targets. Scientists had specific questions. The answers that came back included several that nobody had thought to ask. Jupiter had rings. Before Voyager 1, Saturn was the ringed planet. That was not a casual assumption or a gap in observation. It was the consensus of centuries of telescope work by skilled astronomers using progressively better instruments. Nobody had detected a ring structure around Jupiter because, from Earth, there was no ring structure to detect. The rings are thin, dark, and made of fine particles that scatter very little light. Viewed from the distance of Earth's telescopes, they are effectively invisible against the brightness of Jupiter itself. Voyager 1 found them not because anyone had designed the encounter to look for them, but because the cameras were pointed in the right direction at the right moment and the data came back showing something that should not have been there. A thin ring system confirmed. The outer solar system's inventory of ringed planets had just doubled without warning. That same encounter returned images of two moons that had no names because they had no catalogue entries. Thebe and Metis were found in the Amalthea region, orbiting close enough to Jupiter that Earth-based telescopes had never been able to resolve them from the planet's glare. They were simply too small and too close, drowned out by a body more than 1,000 times Earth's volume. They had been there for billions of years. Nobody had counted them. The solar system in 1979 turned out to contain more objects than any prior survey had measured, not because astronomers had been careless, but because the resolution required to find those moons could only be achieved by an instrument physically present in the Jovian system. What the catalogue said was complete was not complete. The Great Red Spot was supposed to be understood. It had been observed for at least 4 centuries, since the 1600s, and by 1979 it was the best studied feature on any planet other than Earth. Models of it existed, its approximate diameter was known. What was not known was what it actually was in 3 dimensions. Voyager 1's imagery resolved the spot as a standing vortex with genuine vertical structure, not a surface marking, not a flat atmospheric banding artifact, but a storm system with depth and internal dynamics. Wind speeds at its edges exceeded 400 kilometers per hour, and even that figure describes only the perimeter. The internal structure showed a system rotating in tight, organized circulation, sustained not by seasonal forcing or temporary pressure differences, but by the persistent dynamics of Jupiter's atmosphere itself. Earth's most powerful hurricanes are temporary. They form, intensify, and dissipate over days or weeks. The Great Red Spot has been doing what Voyager 1 imaged it doing for at least 4 centuries, possibly longer. Comparing the two is comparing a match flame to a furnace burning since before European contact with the Americas. Then there was Europa. Europa is the second of Jupiter's 4 large moons, and from Earth it appeared as a bright, featureless sphere, one of the smoothest bodies in the solar system, covered in ice. Smooth, because impact craters should have been visible if the surface was old and static, and the absence of large craters implied either a young surface or one that had been continuously reshaped. Voyager 1's imagery revealed why. The surface of Europa is crossed by a network of long linear fractures, lines and bands running across the ice in intersecting patterns that extend for hundreds of kilometers. They are not impact features. They are not tectonic in the way Earth's plate boundaries produce faults, because Europa has no plate tectonics. The fracture geometry is consistent with a shell of ice floating above a liquid layer, flexing and cracking as tidal forces from Jupiter periodically deform the body's interior. The same gravitational mechanism that drives Io's volcanism, the orbital resonance between Europa, Io, and Ganymede, all locked in their precise 1-2-4 relationship, would deposit heat inside Europa too. Not enough to melt rock, enough to melt ice. The hypothesis that emerged from Voyager 1's imagery was specific. Beneath Europa's fractured surface, a liquid water ocean, not a thin film. A global ocean kept liquid by continuous tidal heating, insulated from space by the ice shell above it. The hypothesis was not confirmed by Voyager 1 that precision matters. What Voyager 1 provided was the visual evidence that prompted the hypothesis and made it credible. The cracks pointed toward a subsurface ocean, the way cracks in Arctic sea ice point toward water moving beneath. The Galileo spacecraft, which arrived at Jupiter in 1995 and spent 8 years in orbit, would substantially strengthen that case, measuring magnetic field perturbations consistent with a conductive liquid layer below the ice. But Galileo was 16 years in the future. In 1979, Voyager 1 returned images of a fractured moon and left planetary scientists with a question they could not answer with what they had. Step back and take account. At a single planet, during a single flyby spanning weeks, Voyager 1 found a ring system nobody expected, added 2 moons to the catalogue, confirmed that the solar system's most famous storm is a 3-dimensional structure far more complex than any model described, and produced imagery of a second moon that raised the possibility of a liquid water ocean beneath its surface. None of these were the mission's primary objectives. Io's volcanoes were not on the list either. The instruments were running, the data was flowing, and the universe was declining to behave the way the models said it should. This is not a pattern that ends at Jupiter. It is the pattern. Every assumption the pre-Voyager picture of the solar system had assembled about rings, about moon inventories, about storm dynamics, about what the word frozen means when applied to a moon failed on contact with data from a machine that was actually there. The scientific literature before 1979 described a Jupiter system built from inference. What came back from the flyby described a different system entirely. The spacecraft had not yet reached Saturn. It had not yet turned its cameras backward toward Earth. It had not yet crossed anything. And already the outer solar system was proving itself stranger, larger, and more structured than anyone standing on the ground had been able to see. What would happen when Voyager 1 went even further? Saturn had been the most visually studied planet in history. Galileo first saw its rings in 1610, though he mistook them for 2 flanking moons. Christian Huygens resolved them correctly in 1655. By 1979, 3.5 centuries of increasingly precise telescope work had produced a consensus picture. Saturn had a handful of broad, distinct ring bands, the A ring, the B ring, the C ring separated by gaps, the most prominent of which was the Cassini division, a dark band wide enough that early astronomers thought it was empty space. The system was mapped, understood in its broad architecture. The details, it turned out, were not what anyone had mapped. On the 12th of November 1980, Voyager 1 reached closest approach to Saturn at approximately 124,000 kilometers from the cloud tops. What the cameras returned was structurally incompatible with the consensus picture. The 3 broad bands were not 3 broad bands. They were thousands. Individual ringlets, tightly packed, each a distinct structure with its own density, composition profile, and orbital behavior. The rings were not a smooth sheet of material, they were a system of extraordinary complexity, organized at a scale that centuries of telescopic observation had completely missed, because the resolution required to see individual ringlets can only be achieved from inside the Saturnian system. One specific feature refused explanation then. It still does. Inside the B ring, the brightest and broadest of Saturn's ring structures, Voyager 1 imaged dark radial markings extending outward from the inner edge like spokes on a wheel. They appeared and disappeared over timescales of hours. They rotated with the ring material in some respects, but not others. This was immediately strange. Ring particles at different orbital distances travel at different speeds under Keplerian dynamics, so any radial feature should shear apart quickly. The spokes did not shear. Something was holding them together, or regenerating them, faster than orbital mechanics could destroy them. The leading explanation attributes them to electromagnetic forces, electrically charged dust grains suspended above the ring plane by the planet's magnetic field, maintaining alignment through electromagnetic rather than gravitational coupling. But the precise mechanism, the conditions required, the life cycle of individual spokes, these remain active research questions. The most closely observed ring system in history produced a feature that 4 decades of subsequent study have not fully resolved. Then Titan. Titan was not a secondary target. It was the reason Voyager 1 was at Saturn at all, in the sense that the Titan flyby was given priority that determined everything else. Titan is the only moon in the solar system known before Voyager arrived to possess a substantial atmosphere. What kind of atmosphere? How dense? What composition those were? Open questions. Scientists wanted them answered. The closest approach to Titan was set at approximately 6,490 kilometers closer than any other body in Voyager 1's entire mission, closer than Jupiter, closer than Saturn itself. The instruments were aimed, the trajectory was set, and the price of that choice had already been calculated before the spacecraft reached the Saturnian system. What Voyager 1 found inside Titan's atmosphere was a world running on chemistry that Earth scientists recognized but had never seen operating at this scale. The atmosphere was nitrogen-dominated, greater than 95% nitrogen, making it more similar to Earth's atmosphere in bulk composition than any other world in the solar system. But the resemblance ended there. Sunlight breaking apart nitrogen and methane in the upper atmosphere drove complex organic synthesis, producing molecules called tholins, reddish-brown polymers, that exist almost nowhere else in the solar system alongside a suite of other hydrocarbons. The atmospheric pressure at the surface was approximately 1.5 times Earth's at sea level. The surface temperature was approximately minus 179 degrees Celsius. At that temperature, methane can exist as a liquid. The chemistry pointed toward lakes, possibly seas, of liquid methane and ethane sitting on a surface nobody could see. Voyager 1 could not see it. The thick orange photochemical haze that gave Titan its amber color was not a thin veil. It was a complete obstruction. The cameras that had resolved individual ringlets in Saturn's ring system, that had captured volcanic plumes on Io, could not penetrate the haze to photograph a single surface feature on Titan. The moon revealed its atmosphere and hid everything beneath it. Voyager 1 left Titan with a detailed atmospheric measurement and no surface map, a result that told scientists what was happening chemically while withholding any direct view of where it was happening. The measurements were worth what they cost. The cost was precise and known in advance. Choosing to fly Titan at 6,490 kilometers required a specific trajectory. That trajectory bent Voyager 1's path northward, out of the plane of the solar system, the ecliptic, at approximately 35 degrees. Geometry is not negotiable. Once the spacecraft crossed Titan and its trajectory was set, Uranus was unreachable. Neptune was unreachable. The grand tour that the 175-year planetary alignment had made theoretically possible, Jupiter to Saturn to Uranus to Neptune in a single continuous arc, was reduced by one deliberate choice to Jupiter to Saturn, and then outward into nothing in particular. Voyager 2, travelling a different trajectory, would complete the full tour. Voyager 1 would not. That outcome was not an accident or a failure. It was the decision made consciously by people who ran the numbers and chose Titan. What came after Saturn was not a destination. The mission had been designed to reach the outer planets. Both outer planets within Voyager 1's reach were now behind it. JPL extended the mission formally, the Voyager Interstellar mission, but the extension was not a new assignment with new targets. It was a commitment to keep listening to a spacecraft heading outward regardless, across distances no instrument had ever traversed, toward a boundary that existed only in theory and that nobody knew how to confirm when it was crossed. The instruments aboard Voyager 1 were built for planetary flybys. They were calibrated for the inner heliosphere. They had no operational specifications for the Termination Shock, the heliosheath, or the Heliopause. Nobody had written those specifications because nobody had ever needed them. The spacecraft was going somewhere its designers had not designed it to go, carrying instruments that had not been built for where it was going, into conditions that could only be guessed at from physical models constructed entirely from the inside. Saturn receded in the cameras. The rings shrank to a point. Titan's orange disk faded into darkness, and Voyager 1 kept moving. 13 years after launch, with Saturn long behind it and nothing resembling a destination ahead, Voyager 1 received an unusual command. The request came from Carl Sagan. He had been making it for years. The idea was straightforward. Before the cameras were shut down permanently to conserve power, turn them back toward the inner solar system one final time and photograph Earth from where the spacecraft now stood. A farewell image, a record of what the machine had left behind. The resistance he encountered was not bureaucratic stubbornness. It was rational. At 40.5 AU from Earth, the planet was not a scientifically useful photographic target. No new data about Earth's geology, atmosphere, or composition would come from an image taken at that distance. The cameras drew power. Other instruments, the ones still doing real science, still measuring particle fields and magnetic environments, needed that power. There was a legitimate argument that turning the cameras on for a portrait served no scientific purpose. Sagan did not dispute the logic. He persisted anyway. On the 14th of February 1990, the cameras were turned on for the last time. Voyager 1 was approximately 6.06 billion kilometers from Earth. The spacecraft swept its cameras across the inner solar system and assembled a mosaic. In that mosaic, Earth is visible. It is a point of light. It occupies exactly 0.12 pixels in the image frame. Not approximately 0.12, not roughly a pixel, exactly 0.12 pixels. That number comes from the actual pixel count of the actual image, not from a calculation designed to produce a moving result. The planet that generated every human civilization, every war fought, and every peace negotiated, every piece of music composed, and every scientific paper published, including the papers that designed the machine. Now, taking this photograph is 0.12 pixels wide. It is smaller than the diffraction artifacts caused by sunlight scattering inside the camera lens. Earth appears as a pale blue mote, suspended in a band of scattered light, almost indistinguishable from an artifact, identifiable only because the engineers knew precisely where to look. Immediately after the mosaic was complete, the cameras were shut down. They have never been turned on again. This was not a temporary suspension. It was the end. The power briefly redirected to the cameras returned permanently to the instruments capable of measuring what lay ahead. Voyager 1 has been travelling for 35 years since that moment, without once looking back. The image taken on the 14th of February 1990 is the last thing those cameras ever saw. 4 years after the photograph, Sagan delivered a spoken address drawing on the image. He published it in his 1994 book, also titled Pale Blue Dot. The passage has since travelled further than most writing does. It appears in climate speeches and eulogies, in museum installations and graduation addresses, in arguments about war and arguments about what human beings owe each other. The words, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. On a mote of dust suspended in a sunbeam." What those words did was not explain the image scientifically. The science is in the pixel count. What Sagan did was translate a measurement into an emotional fact. The felt sense of what the measurement means when you hold it against everything that has ever happened on the surface being measured. For a portion of the people who have encountered that passage, the felt sense of Earth's position in space shifted. Not its astronomical classification, its weight. The photograph changed what it feels like to know where we are, which is a different kind of knowledge than knowing the distance in kilometers. The history of instruments that altered human self-perception is short. The telescope, the microscope, the first photographs of Earth from orbit taken during the Apollo missions, which produced the blue marble, an image of a fully illuminated Earth against black space that entered the visual vocabulary of the environmental movement almost immediately. Voyager 1 extended that lineage from low Earth orbit to the outer edge of the planetary system, and the effect was different in kind. The blue marble shows a world. The pale blue dot image shows a pixel. That difference is not a matter of image quality. It is a matter of scale. The blue marble makes Earth look whole and beautiful and isolated. Taken from 6.06 billion kilometers, the same planet becomes incidental not because it is, but because that much distance does that to a world, to any world, to everything. The image is not a statement about Earth's value. It is a statement about what value looks like from far enough away. The cameras are gone now. They will not be turned on again. There is no plan, no reserve power, no engineering path that would allow it. What Voyager 1 carries into the dark from this point forward is not the ability to look, it is the ability to measure. Particle counters, magnetic field sensors, a plasma wave instrument. These are the tools the spacecraft has left, and they are aimed forward, not back. The question the film has been building toward is not a sentimental one, it is a physical one. Between Voyager 1 and the boundary of the heliosphere lies a region nobody has directly sampled, at conditions no instrument built before this spacecraft was designed to handle. The edge is real. The instruments are aging, and the machine is still moving. What exactly was waiting at that boundary, and what it looked like when the crossing finally happened, is a different kind of story than anything the cameras ever captured. The sun does not simply sit in space. It breathes out. Every second of every day, the sun expels a continuous stream of charged particles, electrons, protons, the stripped nuclei of atoms accelerated outward in every direction by the corona's extreme temperatures and the sun's own magnetic pressure. This is the solar wind. It does not gust intermittently. It flows constantly at somewhere between 300 and 400 kilometers per second under ordinary conditions, faster during solar storms, sustained across distances that dwarf anything in the planetary system. By the time it reaches Earth, it has already traveled 150 million kilometers. It does not stop at Earth. It does not stop at Mars or Jupiter or Saturn. It keeps going. The solar wind inflates a bubble. Astronomers call it the heliosphere. It encompasses the entire planetary system and extends far beyond, past the orbit of Neptune, past the Kuiper Belt, out into a region where no planet orbits and no telescope from Earth's surface has ever resolved anything clearly. Inside this bubble, the sun's magnetic field dominates. It determines which particles can penetrate and which are deflected. It shapes the radiation environment in which every planet in the solar system exists. Inside the heliosphere, the physics of space are solar physics. The sun sets the terms. Outside the heliosphere is something else entirely. The interstellar medium, the material filling the space between stars, was not made by our Sunday. It was shaped over billions of years by other stars, their winds, their deaths, the shock waves of supernovae that exploded before the solar system formed. Its magnetic field is the galaxy's magnetic field, not the sun's. The plasma drifting through it has never been touched by solar radiation. It is, in the most literal sense, a different physical regime. Two regions, adjacent, shaped by entirely different forces, separated by a boundary called the heliopause. The heliopause is where the outward pressure of the solar wind finally equals the inward pressure of the interstellar medium pressing back. It is not a wall, it is not a membrane with a precise thickness. It is a pressure surface, the point where two forces reach equilibrium, each pushing against the other. Cross it in one direction, and the sun's influence gives way to everything the galaxy has been building for billions of years. But the heliopause does not stay in one place. The sun's output varies on an approximately 11-year cycle. During solar maximum, when activity peaks and coronal ejections and solar storms are frequent, the solar wind intensifies more particles, more pressure, pushing the heliopause outward. During solar minimum, the sun quiets, the solar wind weakens, interstellar pressure gains ground and pushes back in. The heliosphere expands and contracts, breathing to the rhythm of the sun's own cycle. This is not a minor fluctuation. The heliopause can shift its position by several astronomical units, depending on where in the solar cycle the sun happens to be. This matters because Voyager 1 was going to cross it. And anyone trying to read that crossing from the instruments would need to determine whether a change in the data meant the spacecraft had passed through the boundary or whether the boundary had simply moved. Before the boundary, there is a warning layer. At approximately 94 astronomical units from the Sun, well beyond the realm of any planetary body, the solar wind encounters a physical crisis. It has been travelling supersonically since it left the corona. No force has stopped it. But the accumulated pressure of the interstellar medium pressing inward from every direction is enough to create a standing shockwave. At this shockwave, called the termination shock, the solar wind's velocity drops abruptly from 300 to 400 kilometers per second to approximately 20 kilometers per second. Supersonic to subsonic, in a transition region rather than an instantaneous line. The solar wind does not reverse. It does not dissipate. It slows, compresses, and heats. Past the termination shock, it continues outward. But now it is sluggish and turbulent, no longer the organized, coherent stream that fills the inner solar system. It mixes with particles that have leaked inward from interstellar space, trapped and bounced between the termination shock and the heliopause in a compressed zone called the heliosheath. This is not a thin transition. The heliosheath is a region of genuine thickness, turbulent and structured, where two regimes interpenetrate without yet fully giving way to each other. Voyager 1 would spend years inside it. Think of it as an atmosphere. The solar system has a layered outer atmosphere, the termination shock as the upper boundary of organized solar wind, the heliosheath as a thick, turbulent middle layer, and the heliopause as the outer skin, where solar influence finally surrenders. Inside that skin, the sun's domain. Outside it, the galaxy. For the full span of human civilization, every telescope built, every astronomical measurement made, every model constructed, the heliopause existed only as a calculated boundary. Scientists inferred its position from the behavior of the solar wind, from the trajectories of cosmic rays entering the inner solar system, from indirect signatures in the ultraviolet glow of hydrogen atoms scattered through the heliosphere. The models were sophisticated, the parameters were constrained by decades of data. But the heliopause itself, the actual surface, the physical pressure equilibrium between the Sun and the galaxy, had never been measured directly. Nobody had put an instrument there and taken a reading. Nobody had crossed it. No one knew precisely what the instruments would find when crossing finally happened. The models described what should be on the other side: different plasma density, different magnetic field orientation, galactic cosmic rays arriving at their full unfiltered intensity. These were predictions. They had never been tested. And the machine, approaching the boundary, was running on the power equivalent of a few light bulbs, carrying instruments designed for a different mission in a different decade, one of which, the most critical one, had already been silent for 32 years. The edge was real. The physics were settled. What was not settled, what could not be settled until the crossing actually happened, was what the crossing would feel like from the inside, and whether anything on board would still be listening when it did. December 2004. Voyager 1 crosses a line nobody has ever crossed before. Not the heliopause, not yet. What it crosses is the termination shock, the first hard physical boundary of the outer heliosphere at approximately 94 astronomical units from the Sunday. That translates to roughly 14.1 billion kilometers. No spacecraft had ever reached that distance and returned a signal precise enough to describe what was happening there. Voyager 1 did. The crossing was not a moment. It was a recognition. It took weeks to confirm, pieced together from multiple instrument streams reading different physical signatures simultaneously. The low-energy charged particle instrument tracked shifts in particle energy spectra. Magnetic field sensors recorded changes in field strength and orientation. Particle flux data showed the balance between solar energetic particles and galactic cosmic rays beginning to shift. No single reading was definitive. The aggregate was. What the instruments described was a deceleration unlike anything recorded in the outer solar system. The solar wind had been travelling at 300 to 400 kilometers per second supersonic, organized, continuous, since it left the sun's corona. At the termination shock, that speed collapsed to approximately 20 kilometers per second. That is not a gradual fading. That is a standing shockwave, where the outward pressure of the solar wind meets the accumulated resistance of the interstellar medium pressing back. The wind did not stop. It did not reverse. It compressed, heated, and emerged on the other side sluggish and turbulent, stripped of its organized structure. A deceleration from 400 to 20 kilometers per second is the difference between a supersonic aircraft and a bicycle, in a medium with no friction across the boundary of the sun's domain. The geometry of that boundary surprised the team. The termination shock is not a clean sphere surrounding the solar system at a uniform distance. It spans a broad zone, anywhere from roughly 75 to 100 astronomical units depending on direction, dented and asymmetric. Its shape distorted by the interstellar magnetic field pressing against the heliosphere from outside. From inside the bubble, Voyager 1 had no direct way to measure that external field. The spacecraft could feel the result without seeing the cause. The boundary it crossed had a form determined partly by forces it could not observe. That asymmetry introduced a complication the data had already hinted at. Some sources record a possible earlier crossing event at approximately 85 astronomical units, nearly a year before the December 2004 confirmation. If that event was real, it would represent the heliosphere's breathing behavior in action, the solar minimum weakening the solar wind, the interstellar medium pressing the termination shock inward, and Voyager 1 briefly encountering the shock before finding itself back in heliospheric conditions as the boundary expanded outward again with renewed solar activity. The spacecraft potentially crossed the termination shock, retreated from it, and crossed it a second time. Not because the spacecraft moved erratically, but because the boundary itself moved. The December 2004 crossing at 94 AU is the confirmed accepted figure. The earlier event remains flagged, unresolved, a reminder that the heliosphere's outer skin is not fixed geography. Past the termination shock, Voyager 1 entered the heliosheath. The heliosheath is not a void. It is the turbulent compression zone between the termination shock and the heliopause, the region where slowed solar wind and particles that have leaked inward from interstellar space mix without either regime fully dominating. It is thick, structurally complex, and had never been sampled by any instrument before Voyager 1 arrived inside it. The spacecraft spent approximately 8 years traversing this zone, from roughly 2004 through 2012. 8 years of data from a physics environment that had existed in models only. Those were not holding years. The instruments were active, and what they recorded was a region far more complicated than pre-crossing models had assumed. Particle distributions were inconsistent with simple compression. Magnetic field behavior showed structure the models had not predicted. The heliosheath was not a thin, well-behaved boundary layer. It was a region with its own internal physics, and Voyager 1 was the first instrument ever positioned inside it to take a reading. The Termination Shock crossing changed the question the mission was asking. Before December 2004, the central uncertainty was whether Voyager 1 would detect a meaningful boundary at all, whether the instruments that had survived nearly 3 decades of travel would return readings clear enough to describe the heliosphere's outer structure. The Termination Shock resolved that. The boundary was real. The instruments could read it. The deceleration signal had been unambiguous in aggregate, and the spacecraft had survived the transition with its core systems intact. After December 2004, the question was different. It was no longer whether, it was when. When would Voyager 1 reach the Heliopause, the true edge, the pressure surface where the sun's influence finally surrendered to the interstellar medium? And when it did, would the instruments still functioning after nearly 5 decades of operation be sensitive enough, stable enough to recognize what they were passing through? The Plasma Science Instrument, the device built specifically to answer that second question, had been dead since 1980. It would not be there for the Heliopause crossing. Whatever confirmation came would have to come from somewhere else. Voyager 1 pressed outward through the heliosheath, the sun behind it, the Heliopause ahead, the instruments still running, the signals still travelling 22 hours each way back to Earth. The machine, designed for 5 years, was 27 years old when it crossed the Termination Shock, and it was not done. By 2011, Voyager 1 had been in the heliosheath for 7 years. The instruments still running, the low-energy charged particle detector, the magnetometer, the cosmic ray subsystem, the plasma wave instrument built by Don Gurnett at the University of Iowa were returning data from a region no model had been calibrated against. And then the data changed. Not gradually, in steps. Beginning in 2011 and accelerating through the first half of 2012, Voyager 1's cosmic ray instruments recorded sudden, sharp increases in galactic cosmic rays, high-energy particles arriving from outside the heliosphere, from the galaxy beyond. Simultaneously, the solar energetic particles, the lower energy particles generated by the sun and dominant throughout the heliospheric interior, dropped sharply. Then both readings partially reversed. Then the pattern repeated. Galactic rays up, solar particles down, partial reversal, repeat. The data looked like a staircase descending towards something, but the team could not agree on what the bottom of the staircase was. The ambiguity was genuine, not a failure of attention. 3 different physical situations could produce exactly that pattern. The first, Voyager 1, was oscillating near the heliopause as the boundary itself moved. The heliosphere breathes with the solar cycle, solar maximum pushes the heliopause outward, solar minimum allows interstellar pressure to push it inward. If Voyager 1 was sitting near the boundary while it shifted position, the spacecraft would move in and out of heliopause-adjacent conditions without ever fully crossing. The staircase would represent proximity, not transit. The second, the heliopause has layers. Standard models treated it as a relatively clean pressure surface, solar wind on one side, interstellar medium on the other, a transition measured in thousands of kilometers. But if the boundary had internal structure, if it was laminated rather than sharp, the staircase could represent a spacecraft moving through nested transition zones, each with its own particle signature, none of them the final crossing. The third, the crossing had already happened. The staircase was the aftermath of a boundary already behind the spacecraft, its reversal structure a feature of the turbulent near Heliopause environment rather than evidence of oscillation. 3 interpretations. Identical data, no way to distinguish them from the readings available. Into this argument came a 4th possibility, proposed with enough physical reasoning to be taken seriously: the magnetic highway. The concept described a previously uncharacterized transition zone where magnetic field lines from inside and outside the heliosphere reconnected at the boundary, creating pathways along which energetic particles from the heliospheric interior could stream outward while galactic particles streamed inward. In this region, neither heliospheric nor interstellar, but a mixed boundary layer with its own internal logic, the particle environment would look exactly like what Voyager 1 was recording. The magnetic highway was not a metaphor. It was a proposed physical structure, and it offered a coherent alternative to the simple Heliopause crossing interpretation. Some members of the science team considered it the most likely explanation. Ed Stone did not publicly announce a Heliopause crossing in 2011 or in the first half of 2012. The professional stakes of that restraint were real. If Stone announced Voyager 1 had crossed the Heliopause and the heliosphere then expanded back outward as the solar cycle shifted, pushing the boundary past the spacecraft's position and returning it to heliospheric conditions, the credibility of the announcement would be gone, and with it a piece of the credibility of the mission's final chapter. The heliosphere had moved the termination shock before. It could move the heliopause too. Not everyone on the science team shared Stone's caution. The disagreement was professional, collegial in the way scientific disagreements between colleagues usually are, and documented. Different instruments carried by the same spacecraft were producing data that their principal investigators interpreted differently. The cosmic ray team read the staircase as evidence of crossing. The magnetometer team had their own concerns. The plasma wave team was watching for oscillations that might settle the argument, but the oscillations they needed required an external disturbance to trigger a measurable plasma response. That disturbance had not arrived yet, and underneath all of it was a silence that everyone on the team knew about and nobody could fix. The plasma science instrument, built to measure solar wind properties directly, to sample plasma density and velocity in situ, to provide exactly the kind of unambiguous measurement that would cut through the staircase argument in a single reading, had failed in 1980. 32 years before the August 2012 crossing, it was designed to detect. The instrument that would have resolved the debate instantly, that would have shown the team the moment solar plasma disappeared and interstellar plasma replaced it, was gone. It had been gone for longer than some of the mission's current engineers had been alive. What remained was inference. The surviving instruments were measuring particle populations, wave behavior, magnetic field orientation proxies for the plasma environment, not direct readings of it. Each proxy carried its own interpretation problem, its own margin, its own dependence on assumptions about the physical situation the instruments were sitting inside. To know where Voyager 1 was, the team had to model what surrounded it. To model what surrounded it, they needed to know where it was. The crossing that the 25th of August 2012 would later be assigned as its date was not announced on the 25th of August 2012. It was not announced in September. The data arrived, the team studied it. The staircase continued its descent, and eventually the readings did not reverse. The solar energetic particles did not come back. The galactic cosmic ray flux held at its elevated level and stayed there. But the confirmation that the crossing had actually occurred, the measurement that would make announcement possible, had not yet materialized. The spacecraft was almost certainly past the heliopause. The team could not yet say so publicly. What they were waiting for, though most of them did not know it yet in the summer of 2012, was a solar storm launched from the Sun months earlier, crossing the heliosphere at the speed of an interplanetary shockwave. When it arrived, it would disturb whatever plasma surrounded Voyager 1, and the plasma wave instrument would either detect the oscillation signature of the heliospheric interior or of something else entirely. The storm was coming. The answer was inside it. But in the months before it arrived, the scientists watching Voyager 1's staircase data were living inside the most consequential ambiguity in the history of space exploration, with the one instrument that could have ended the ambiguity sitting dead in the dark, 32 years silent, 22 light hours away. The storm arrived in April 2013. It had been launched from the Sun months earlier, a coronal mass ejection, a wave of compressed plasma and magnetic field racing outward at the speed of an interplanetary shockwave. It crossed the heliosphere. It passed through the heliopause. And when it reached Voyager 1, it disturbed whatever medium surrounded the spacecraft, causing the local plasma to ring like a struck bell. Don Gurnett's plasma wave science instrument, built at the University of Iowa in the 1970s, designed to measure oscillations and wave behavior in plasma, detected the response from the frequency of those oscillations. Gurnett's team inferred plasma density indirectly. The number they calculated was approximately 0.08 electrons per cubic centimeter, roughly 40 times denser than the values characteristic of the outer heliosphere, consistent by every available measure with the interstellar medium. The argument was over. The methodology deserves to be stated clearly, because it matters. Inferring plasma density from oscillation frequency is physically valid. The relationship between the two is well understood. But the plasma wave instrument was designed to measure wave behavior, not to stand in for a plasma detector. It was working outside its primary design parameters, and the measurement was indirect. The margin of uncertainty was real, and the scientists said so. What they also said was that the result landed at 40 times the expected heliospheric density. That is not a number that sits inside the error bars of ambiguity. The staircase data, the months of disagreement, the competing interpretations, all of it resolved into a single plasma density figure that placed Voyager 1 unambiguously outside the domain of solar wind. The confirmation had required the Sun's own cooperation. A storm that crossed 18 billion kilometers passed through the boundary the team had been debating for 2 years, and agitated the medium on the other side long enough for one surviving instrument to catch the oscillation. Without that coronal mass ejection, the ambiguity might have persisted for years. There is no second instrument that could have provided equivalent data. The plasma science instrument, built for exactly this purpose, had been silent since 1980. The universe offered one indirect path to the answer, and the team's equipment was positioned to take it. In September 2013, the findings appeared in the journal Science. NASA scheduled a press conference. Ed Stone, Voyager's project scientists since 1972 stood before the cameras at 77 years old, 41 years into a role he had accepted 5 years before the spacecraft launched. His words were unambiguous. This is a historic day for humanity. We have left the solar system. We are now in interstellar space. Don Gurnett spoke at the same conference. His statement was narrower in scope and more precise in its implication. We're in a completely new region. This is plasma that has never been touched by the Sunday. The instrument he had built and nursed through 4 decades of space travel had just produced the measurement that settled one of the most consequential questions in the PACER: history of space science. He spent the final decade of his career watching the reverberations move through the field, new papers, new models built against the data his instrument provided, new debates that his number had made possible. He died in 2024. The announcement should have been the end of the argument. It was not. What Stone's declaration made unavoidable was a definitional question that had been quietly present for years and was now suddenly public. NASA's announcement used the Heliopause as the boundary of the solar system, the point where solar wind dominance ends and interstellar pressure takes over. By that convention, the 25th of August 2012 was the departure date. But the Sun's gravitational reach extends far beyond the Heliopause. The theoretical Oort cloud, the vast reservoir of cometary bodies from which long-period comets are drawn, occupies a zone estimated to reach 50,000 to 100,000 AU from the Sunday. Voyager, 1 inch 2013, was at roughly 121 AU. By gravitational definition, it was not outside the solar system. It was barely past the door. A third definition existed alongside these two: the outer edge of the planetary system, the boundary beyond Neptune where the structured, disc-shaped domain of the planets ends. By that standard, Voyager 1 had crossed the solar system's outer frontier in the early 1990s, over 2 decades before the announcement. 3 definitions. 3 departure dates separated by more than 20 years. None of them wrong, each reflects a genuine physical boundary, each is used by working scientists in the appropriate research context. What the September 2013 announcement did not do was explain which convention it was applying or why. Some researchers objected publicly. The disagreement was not about the plasma density measurement, which nobody disputed. It was about whether the announcement used solar system matched the physical fact the measurement had established. This is not a semantic quarrel dressed up as science. Which boundary you use to define the solar system determines how you characterize the heliosphere's role in shaping the radiation environment Earth life evolved inside. If the solar system ends at the heliopause, then crossing it places you in a physically distinct regime, different particle populations, different magnetic field geometry, different cosmic ray flux. The measurement Voyager 1 made at that boundary is, by this definition, a measurement from outside humanity's home. If the solar system ends at the Oort cloud's gravitational reach, then the same measurement is from deep within it, and the conceptual weight of the announcement changes entirely. That distinction matters to anyone modelling the conditions under which life develops around other stars. The heliosphere is not just the Sun's domain, it is a radiation shield, an electromagnetic buffer between the organised stellar interior and the full intensity of the galactic environment beyond. Understanding where it ends, what that ending looks like, And whether the Sun's heliosphere is typical or anomalous among stellar systems requires precision about which boundary you mean when you describe the solar system's edge. Voyager 1's measurement is the only direct calibration point that exists. The definitional imprecision in the announcement was not a communications failure. It reflected a genuine scientific ambiguity that the measurement itself had forced into the open. What the plasma wave instrument confirmed was narrower than what the press conference announced, and also more important. It confirmed that the plasma surrounding Voyager 1-inch April 2013 had never been processed by the Sunday, that the heliosphere has a real physical boundary measurable in electrons per cubic centimetre, that the storm the Sun launched had travelled across the entire heliosphere, crossed that boundary and produced a reading on the other side. The act of confirmation was itself an act of connection, the Sun reaching out one final time to verify that its domain had ended. What lay beyond that domain, in the medium Gurnett's instrument had just sampled, was a question the story had not yet begun to answer. The plasma density confirmed the crossing. The boundary was real. What should have followed was a clean picture of what that boundary looks like, the magnetic geometry of the edge of the solar system, measured for the first time by an instrument that had actually been there. That picture did not arrive. Every model of the Heliopause carried the same prediction at its centre. The Sun's magnetic field and the interstellar magnetic field originate from entirely different sources, extend across entirely different scales, and are shaped by entirely different forces. Where they meet at the Heliopause, their field lines must change direction. The angular rotation was not a minor detail buried in the mathematics. It was a foundational structural requirement, the kind of prediction that sits at the load-bearing core of a model. Cross the Heliopause, and the field lines rotate. That was the expectation. That was what the magnetometer aboard Voyager 1 was going to confirm. The rotation occurred. It was smaller than every model required. Not absent, smaller. The geometry shifted, but the angular change was suppressed well below what the standard picture demanded. Researchers who had spent careers building models of the heliospheric boundary sat with data their own frameworks could not account for. The measurement was not noisy or ambiguous. The anomaly was clean, and it was not minor. 3 interpretations emerged. None has been ruled out. The first reaches back to the staircase patterns from the months before the crossing the magnetic highway. In this interpretation, Voyager 1 entered a transition zone where field lines from inside and outside the heliosphere reconnect across the boundary, creating a mixed region where the directional contrast between the two domains is genuinely suppressed. If the spacecraft spent time in this zone before fully clearing the Heliopause, the magnetometer would record an averaged blended field, not the sharp directional signature of crossing from one domain into another, but the muted geometry of a place where both domains are entangled. The magnetic highway would explain the suppressed rotation. It would also mean the Heliopause is not the clean dividing line the models assumed, but the outer wall of a more complex structure. The second interpretation does not require a new zone. It requires a more turbulent boundary. The Heliopause breathes the earlier chapters in this story establish that clearly. What follows from that breathing is the possibility that the boundary is not a sharp membrane, but a turbulent, fluctuating interface, thicker and more disordered in its magnetic structure than any model captured. Voyager 1, moving through such an interface, would sample field orientations from both sides in rapid succession, averaging them in time rather than experiencing a clean transition. The suppressed rotation would be the signature not of reconnection, but of a boundary with interior disorder, one that Voyager 1 may have crossed and partially recrossed as the structure moved. The third interpretation does not revise the boundary at all. It revises the interstellar magnetic field itself. Every model of the heliopause was built using indirect observations of the interstellar field measurements made from inside the heliosphere, using starlight polarization, synchrotron radiation from distant electrons, and pulsar dispersion data. Those techniques are valid, but they measure the field from far away, through the very heliosphere that mediates the view. If the interstellar magnetic field in the Sun's local neighborhood is oriented differently than those indirect observations indicated, the predicted rotation at the heliopause would be wrong from the start, not because the boundary misbehaved, but because the input to the model was inaccurate. In this interpretation, the anomaly is not a mystery about the heliopause. It is a correction to what we thought we knew about our immediate interstellar surroundings. 6 years after Voyager 1's crossing, the second spacecraft arrived at the heliopause from a different direction. Voyager 2 crossed in 2018, traveling southward from the ecliptic rather than northward. Its crossing measurements diverged from Voyager 1's in ways the science team did not fully anticipate. The plasma pressure outside the boundary was different. The magnetic field configuration was different. The boundary itself appeared to have a different thickness. 2 spacecraft, 2 crossings, 2 sets of conditions that do not match. 3 explanations compete for this discrepancy. The heliosphere is asymmetric, structured differently at the nose than at other angles, shaped by the asymmetric pressure of the interstellar medium flowing past it. Or the interstellar medium itself varies from place to place, and the 2 Voyagers crossed into slightly different local environments. Or the Sun's activity level differed between 2012 and 2018. The heliosphere expanded or contracted accordingly. And the boundary Voyager 2 crossed was a physically different object than the one Voyager 1 crossed. 6 years of solar cycle change, 2 different trajectories, 2 different boundary states. The discrepancy is real, and none of the 3 explanations can be confirmed or excluded with 2 data points. A separate finding sits beneath the anomaly. The interstellar magnetic field that Voyager 1 has measured directly in the medium, beyond the heliopause, appears more ordered, less turbulent than models built from inside the heliosphere predicted. A smoother, more organized field structure carries specific consequences. Galactic cosmic rays traveling through a well-ordered field follow more predictable trajectories than they would through a turbulent one, which affects how they propagate across the galaxy and how effectively the heliosphere's boundary can deflect or redirect them. It also shapes predictions about what other stellar heliospheres look like from outside, and whether the Sun's immediate interstellar neighborhood is typical of the broader medium or a local condition. That question cannot be answered from a single measurement point. What the measurement establishes is that the models did not predict this level of order, and the reason for the discrepancy is unresolved. The magnetic field anomaly at the heliopause is the central, unsettled result of the most consequential boundary measurement ever made. Not a secondary finding, not a refinement of something already understood. The central result. Voyager 1 is the only instrument that has ever been at that boundary. and what it measured there does not match what humanity's best models said it would find. The one confirmed fact about the edge of the solar system is that the edge does not behave the way we thought. There is no scheduled return visit. No second instrument is on its way. The data that exists is the data that exists, and the anomaly it contains will remain open until something changes, either in the models or in the measurement record. One of those two will have to move first. 9 years after the crossing, the plasma wave instrument found something nobody had assigned it to find. In 2021, researchers analyzing Voyager 1's data stream identified a continuous faint oscillation in the plasma surrounding the spacecraft, present not as a transient spike triggered by a solar event, but as a persistent background feature of the medium itself. The frequency, approximately 3 kilohertz. The instrument team named it a persistent hum. The space between stars is not silent. It carries its own signal, steady and low, independent of anything the sun has done. This was not predicted. The 2013 confirmation had used plasma oscillations triggered by an arriving coronal mass ejection, a disturbance propagating from a star 18 billion kilometers away, shaking the medium long enough to measure. That measurement was a response to an external event. What the 2021 detection revealed was different in kind, a property of the interstellar medium in its resting state. The medium hums without being struck. It has a baseline electromagnetic texture that Voyager 1's instrument can read continuously, as long as the instrument has power to run. The density that produces that hum has been measured at approximately 0.08 electrons per cubic centimetre. Write that out slowly. 8/100ths of a single electron in every cubic centimetre of space. By any scale familiar to human experience, that is indistinguishable from nothing. The air in a room you consider empty contains roughly 10 to the power of 19 molecules per cubic centimetre. The difference is not large, it is categorical. And yet, by the standards of interstellar space, a density of 0.08 electrons per cubic centimetre is measurably higher than the values recorded in the outer heliosphere before the crossing. The interstellar medium is not an absence, it is a thinner version of something. It has a density, a field structure, a frequency at which it oscillates properties that distinguish it from a vacuum as concretely as vapour differs from dry air. The word void is not technically wrong, but it is physically misleading in ways that matter. The medium between stars has been described for so long in the language of emptiness that the language has become a model, and the model is incorrect. Voyager 1's instruments have measured a place with real electromagnetic character, and that character is specific enough to carry a detectable hum at a measurable frequency. The interstellar medium is not what the word void implies. What it contains, in significant quantity, is radiation. Inside the heliosphere, the sun's magnetic field and the outward pressure of the solar wind combine to deflect and attenuate the galactic cosmic ray flux arriving from the rest of the galaxy. The heliosphere is a radiation shield, not a perfect one, but a functioning one with measurable effect. Outside the heliopause, that shielding ends. Voyager 1's instruments, now operating without any heliospheric attenuation, have returned the first direct measurement of galactic cosmic ray intensity at full, unfiltered interstellar strength. The flux is higher, measurably, significantly higher than what spacecraft and instruments inside the heliosphere have ever recorded. The biological weight of that measurement is not peripheral. The radiation environment in which life on Earth evolved was shaped by the heliosphere's shielding across billions of years. The organisms that exist today, including the ones who built the instrument, now making this measurement, developed in a radiation environment, the heliosphere modulated. We have never had a direct calibration of how much modulation the heliosphere actually provides, because no instrument had ever been outside it to compare. Voyager 1 now provides that calibration. The difference between the shielded interior and the unshielded exterior, measured directly, feeds into every model of what conditions a planet needs to sustain complex biology, and into every calculation of radiation exposure for any crewed mission that travels far enough from the Sun to lose that shielding. The interstellar medium that Voyager 1 is sampling is not a local invention. It was shaped by forces operating across timescales that dwarf the solar system's history. Other stellar winds pressing outward from stars that were born and died before the Sun ignited. The remnants of supernovae that seeded the medium with heavy elements and magnetic field structure before any planet here had formed. Magnetic fields generated by the Milky Way's rotation across distances that make the heliosphere's diameter a rounding error. Voyager 1 is one instrument at one location, measuring one moment in a medium with a history measured in billions of years. The sample is honest about its own narrowness, but the narrowness does not diminish what the sample has done. Every model of the interstellar medium built before August 2012 was constructed without a single direct measurement from inside it. Scientists inferred its properties from astronomical observations made from inside the heliosphere, from starlight polarization, from the behavior of radio waves propagating through it across stellar distances, from cosmic ray arrival angles. The methods were valid, the conclusions were reasonable, given the data available. And they were wrong in specific, instructive ways. The density was slightly higher than expected. The magnetic field was more ordered than expected. The medium carries a persistent 3-kilohertz signal that no pre-crossing model predicted. None of these individual discrepancies shatters the field. Together, they confirm the same structural problem. The models were calibrated on inference, not measurement. The interstellar medium was described from outside it for the entirety of scientific history, and the description was close enough to be useful and wrong enough to matter. The sample size problem is real, and it does not dissolve. Voyager 1 has measured one point in one direction at one moment. Voyager 2 provides a second point from a different angle. There are no others. The persistent hum at 3 kilohertz may be a property of the local interstellar medium around the Sun, or it may be a local condition that a different measurement point would not replicate. The density of 0.08 electrons per cubic centimetre may be characteristic of our immediate stellar neighbourhood, or it may vary sharply a few AU in any other direction. Neither question can currently be answered. Both questions matter for understanding how typical or unusual the conditions around the Sun actually are. What Voyager 1 has established, with the instruments it has left, is that interstellar space is a real, textured, measurable place, not an emptiness to transit, not a theoretical category. A medium with density, with field structure, with electromagnetic oscillation at a frequency the instrument can name. It is not what the model said. It is not what the word void suggests. And it is not done being measured, not yet. Not while the power holds and the signal travels home across 22 hours of distance at 160 bits per second. The hum continues. The instruments are still listening. In November 2023, Voyager 1 began transmitting nonsense. The signal was arriving. 22 to 23 hours of travel time, crossing approximately 24 billion kilometers, the carrier wave intact, the spacecraft was alive. But the data it was sending was corrupted beyond reading. Garbled sequences where telemetry should have been. Engineers at JPL could confirm the machine existed. They could not determine what it was experiencing, what its instruments were measuring, or whether any of its systems were failing in ways that required an immediate response. For a spacecraft at the edge of interstellar space, that distinction matters in ways that cannot be recovered. What followed was engineering of a kind that has no clean modern precedent. The team pulled out paper schematics from 1977. Physical manuals, yellowed, some of them the only surviving records of how specific subsystems were wired together. Retired engineers, people in their 80s who had not worked the mission in decades, were contacted and consulted. Some of the knowledge required to diagnose a fault in Voyager 1's computers does not exist in any database. It exists in the memory of people who are aging out of availability as reliably as the RTGs are aging out of power. Suzanne Dodd, Voyager's project manager at JPL, has described the work as archaeology as much as engineering. In November 2023, that description stopped being metaphor. After 5 months of analysis, the team isolated the source. A single corrupted chip in the flight data system responsible for storing approximately 3% of the FDS memory. The chip was not functioning correctly. It was corrupting the data before transmission. The leading explanation is that a high-energy cosmic ray struck the chip and caused physical damage, a particle from the interstellar medium, the same medium Voyager 1 had been measuring, hitting the machine that was measuring it. The spacecraft is being altered by the environment it is describing. That is not a rhetorical flourish. It is what the data suggests. The fix required redistributing the affected software code across the remaining undamaged memory locations on a 46-year-old computer. Every command sent from JPL traveled at the speed of light across 22 to 23 hours of distance. The team then waited another 22 to 23 hours for the response. 45 hours round trip minimum before knowing whether a single command had worked. No simulation, no test environment. The first real trial of each rerouting decision happened on the actual spacecraft in interstellar space, with no second machine to learn from. The procedure succeeded. By April and May of 2024, science and engineering data from all 4 remaining active instruments had been restored. Dodd's words when it was confirmed, "It was the best news I've had since I became project manager." The machine survived, but the arithmetic has not changed. Voyager 1's 3 radioisotope thermoelectric generators lose approximately 4 watts per year. At launch, they produced around 470 watts. By 2025, the estimate is 249 to 260 watts, comparable to a few incandescent bulbs. Sometime in the mid to late 2020s, the output will drop below what the remaining science instruments require to operate. When it does, the instruments will go dark. One by one, or together, depending on how the power management decisions fall. After that, the signal will still travel, but there will be nothing left to report. There is no repair mission being planned. No successor spacecraft is on a trajectory to reach these distances. When Voyager 1 goes silent, the direct measurement of the local interstellar medium ends, and there is no date on which it resumes. Aboard the spacecraft, fixed and permanent, is a gold-plated copper disk. Carl Sagan assembled its contents in 1977. Sounds from Earth, music spanning cultures and centuries, greetings spoken in 55 languages, encoded images of the planet and its inhabitants. He described it as a message in a bottle cast into the cosmic ocean with no expectation of reply. That phrase was not modesty, it was precision. The probability of any intelligence intercepting Voyager 1 inch any time frame that would mean anything to human civilization is, by honest reckoning, vanishingly small. The record was not placed aboard because communication was expected. It was placed aboard because a civilization that had built a machine capable of leaving its own solar system decided to mark the fact of its own existence, not for an audience, but for the record. A species that knew enough about its own smallness to name it, and then sent the name outward anyway. When the instruments go silent, the golden record will still be travelling. Interstellar space contains almost nothing capable of destroying the physical object. No weather, no oxidation, no geological forces. The estimated survival time of Voyager 1 as an intact structure is measured in hundreds of millions of years. That duration exceeds the expected remaining lifespan of complex life on Earth, which solar evolution will make increasingly difficult to sustain over the next several 100 million years. The machine humanity built will outlast the conditions that made humanity possible. The longest-lasting artifact is also the farthest one. Those two facts have the same cause: distance from everything that destroys. And so the story arrives where it was always going. A machine weighing less than a mid-sized car, carrying a computer with roughly 70,000 times less memory than a modern smartphone, running on power comparable to a handful of light bulbs, built by engineers, most of whom are no longer alive. That machine crossed the edge of the solar system and transmitted measurements from the other side. The Heliopause magnetic field did not rotate as every model had predicted. The plasma density outside was 40 times higher than the outer heliosphere. The interstellar medium carries a persistent hum at 3 kilohertz that no pre-crossing model anticipated. The boundary between the solar system and interstellar space has layers and fluctuations that existing theory had not accounted for. Voyager 2's southward crossing in 2018 found different conditions than the northward crossing in 2012. And the three competing explanations for that discrepancy remain unresolved. We have one instrument in one direction from one moment. It has already forced revisions to models built over decades of careful inference. The revisions are not finished. Voyager 1 did not find what it was sent to find. It was sent to the outer planets, and it reached them, and it found things there that changed planetary science permanently. But the discovery that sits outside every category, the mission was designed for the one that required the machine to outlive its own mission description by 4 decades, is the measurement it made at the edge. Not of Jupiter, not of Saturn, of the place where the sun's influence ends and something older and larger begins. That measurement came back at 160 bits per second, across 22 hours of empty space from a machine nobody expected to last 5 years. It is still coming back.